Hey everyone, and welcome. So, I want you to just take a look around you for a second. The desk you're at, the air you're breathing, maybe that cup of coffee. It's all just stuff, right? Well, today we're going to put on our chemistry goggles and figure out what all that stuff really is. We're going to see how chemists classify basically everything in the universe, and you'll see it's way simpler than you might think. All right, so the first thing we have to tackle is a word you see all the time: pure. You see it on orange juice cartons, on honey jars, but to a scientist, that word means something very different. Let's think about this with a classic example. That gallon of milk sitting in your fridge. You'd probably say it's pure, right? Well, a chemist would say, nope, not even close. So, what gives? And here's why. It's a total showdown between two meanings. To most of us, pure just means, nothing weird was added. But in science, it's super strict. It means something is made of only one single type of particle. That milk in your fridge is actually a jumble of water particles, fat particles, protein particles. You get the idea. It's a mixture. So for a chemist, it is definitely not pure. So let's lock this in. A pure substance is a form of matter where every single tiny particle is chemically the exact same as the one next to it. Think of a pure gold bar. It's just gold atoms, over and over and over. Now that we've got that down, let's see how this one idea helps us classify everything. So when a chemist gets a new substance, how do they start sorting it out? They don't need some fancy machine, at least not at first. It all starts with one single, really big question. And this is it. This is the question: can you separate it into different parts using physical methods? And by that I mean simple stuff like using a filter or boiling something away or even just picking bits out. The answer to this question, yes or no, sends you down two totally different paths. And here are those two paths. If you answered yes, you can physically separate it. Then congratulations, you've got yourself a mixture. If you answered no, there's no physical way to break it down, then you are holding a pure substance. This is the first and most important split in all of chemistry. All right, let's go down that mixture path first, because honestly, most of the stuff you and I deal with every single day, yep, it's a mixture. From the pizza you ate last night to the soda you're drinking right now. So what is a mixture? It's just two or more pure substances that are physically mixed together, but not chemically joined. That's the key. They're just hanging out in the same space. And because they aren't bonded, you can use physical means to get them apart again. You can also mix them in any ratio, a little bit of sugar in your tea or a whole lot. Now, mixtures themselves come in two main flavors. On one side, you've got homogeneous mixtures. The key word here is homo, meaning same. They look completely uniform all the way through, like air or salt fully dissolved in water. On the other side, you've got heterogeneous mixtures. Hetero means different. With these, you can actually see the different parts. Think about a pizza. You can see the crust, the sauce, the cheese. Or a salad dressing with oil and vinegar. You see those layers, right? Okay, here's a super important vocabulary word. In chemistry, we have a special name for those homogeneous mixtures. We call them solutions. Now, when you hear solution, you probably think of a liquid, but that's just one piece of the puzzle. The truth is, solutions can be solids, liquids, or gases. For example, brass is a solid solution of zinc metal dissolved in copper metal. We call that an alloy. The air we're all breathing is a gaseous solution of oxygen and other gases dissolved in nitrogen. And of course, you've got your classic liquid solutions, like the carbon dioxide gas dissolved in water to make soda. Now, inside every single solution, there are two key players. You have the solvent, that's the main ingredient, the one doing the dissolving. And then you have the solute, that's the stuff that gets dissolved. So if we make salt water, water is our solvent and the salt is our solute. Simple as that. All right, pop quiz time. Let's think about that can of soda again. We know it's a solution, and the water is definitely the solvent. So what's the solute? What's the thing that's dissolved in the water? It's the carbon dioxide gas. That's what gives it all those bubbles and that fizzy kick. Okay, things are going pretty well. But what about those mixtures that try to trick us? I'm talking about things like milk or fog. They look uniform, kind of like a solution, but they're hiding a secret, and all you need to find it is a beam of light. So this is the puzzle, right? How can a scientist tell the difference between a real, true solution, where the solute particles are tiny and totally dissolved, and a sneaky imposter, like milk, where bigger particles are just floating around. This is where we meet a new friend, the colloid. Milk is the perfect example. The little clumps of fat and protein are way too small for you to see with your eyes, but they're much, much bigger than a single dissolved salt particle. And that size difference is everything. And this amazing light scattering trick has a name. It's called the Tyndall effect. It's our secret weapon for telling the difference between a colloid and a true solution. And I promise you, you have seen this in real life. You know when you're in a forest and you see those beautiful beams of sunlight cutting through the misty air? You're not seeing the light itself. You're seeing the path of the light as it bounces off the tiny water droplets in the mist. That's the Tyndall effect in action. So, here's how it works in the lab. If you shine a laser pointer through a true solution, like salt water, the beam just passes clean through. You can't really see it in the water. But shine that same laser through a colloid, like milk, and boom! The particles scatter the light all over the place, and you can see the beam's path perfectly clearly. Okay, so we've explored the entire world of mixtures. To finish our map of all matter, let's jump back to that other big path from our flowchart: pure substances. Pure substances also break down into two main types. First, you have elements. These are the absolute building blocks of the universe, everything you see on the periodic table, like a bar of pure iron or a tank of pure copper. You can't break them down into anything simpler. Then you have compounds. This is what you get when two or more elements chemically bond together. The key word is bond. Unlike a mixture, they're stuck together in a fixed ratio, like two hydrogens and one oxygen always making water, H2O. And when they bond, they form a totally new substance with brand new properties. And that's it. That's the whole flowchart. By asking just a couple of simple questions, can I separate it physically? Does it look the same throughout? Does it scatter light? You can now classify pretty much any piece of matter you can find. So, for your final test, let's put this into practice. Just look around the room you're in. I want you to find one homogeneous mixture, one solution, and one heterogeneous mixture. I bet you can find a bunch. Once you start looking at the world this way, you'll realize chemistry is absolutely everywhere.